Hi everyone. Today I would like to give a tutorial on Thompson sampling, and I will mention on how this algorithm works and why it works. So uh, Thompson sampling is a strategy proposed for the multi-arm bandit problem. So first I would like to mention quickly about the multi-arm bandit problem. So assume that you have multiple slot machines, and each time you pull uh, the arm of a slot machine, you obtain a certain reward. Uh, and we can model the reward obtained from each slot machine by a certain probability distribution. And uh, the problem is that we don't know the distributions associated with the slot machines. Uh, and therefore, we need to infer on these distributions from the data we observed by pulling the arms of these slot machines. Uh, our ultimate goal is to pull the slot machine with the highest expected reward or return. So one of the uh, strategies, one of the popular strategies is the Thompson sampling strategy, and I will talk about that in the next slide. Before moving on to the method itself, I would like to introduce some basic notation so that I can explain this algorithm in a concise way. So I will use K to denote the number of arms or slot machines, and I will use mu I to denote the expected return we obtain from the slot machine number I, and I will use theta to denote the vector whose elements are these expected return of the slot machines. So since Thompson sampling is a Bayes algorithm, we assume a prior on this vector theta uh, at the start. And if we don't have any knowledge on this theta, we can reasonably assume a uniform distribution on each of these mean values. So as we pull arm, we collect data on these arms, and which I denote by D. Based on this data and assumed prior, we can update our belief on this theta by computing its posterior distribution using the well-known Bayes formula as given in the slide. A pseudocode for the Thompson sampling algorithm is given in this slide. It looks kind of complicated, but it actually consists of very simple steps, and I will go over each of them one by one. First, as input, we give a prior distribution over the theta that I have mentioned in the previous slide. And if we don't have any idea about how the expected return of each slot machine is distributed, we can input a uniform distribution for each of the slot machines. And we also input the time horizon denoted by capital T, which is the total number of times we want to play these slot machines. So small t represents the current round we are in. So if small t is equal to 10, that means we have already played the slot machines 9 times, and we are at the 10th play. So in the third step, The algorithm constructs a posterior of theta based on the prior distribution we have inputted and the observed rewards in the past t-1 rounds using the Bayes rule. So in the fourth step, algorithm samples from this posterior distribution to obtain a sample for each slot machines. And in the fifth step, algorithm recommends the slot machine with the highest sample value and recommends it to the user. And after user plays the slot machine, it inputs the reward she obtained from this machine back to the algorithm. And algorithm updates its posterior based on this new sample, new reward observation, and algorithm continues like this until we reach the time horizon. To understand how Thompson sampling works, let's see a simple example. Assume that we have only two arms distributed according to the Bernoulli distribution, with the first arm having an expected return of 0.9 and the second arm having an expected return of 0.1. Clearly, arm 1 is a better arm, and we would like to pull arm 1 as much as possible. Initially, since we don't have any data on these reward distributions, our posterior is the same as the prior distribution. And as I mentioned before, if we don't have any knowledge on how the expected return of each arm might be distributed, then it's reasonable to assume that the expected return is distributed according to a uniform distribution. And as we can see in the slide, indeed, the prior is uniformly distributed for both arms. And Thompson sampling samples from this prior distribution and assume that the sample for the first arm is 0.4 and the sample from the second arm turns out to be 0.6, in which case Thompson sampling recommends us to pull the second arm. And since the second arm has a low expected return, it's much more likely to give a zero reward when it's pulled. And let's assume that this is indeed the case, and we obtain a zero reward when we pull this arm. And then according to this data, we update our posterior distribution on arm 2. And as you can see, we update our belief on the expected return of the second arm in a way that the expected return is much likely to obtain a value closer to 0, which makes sense since we observed a reward of 0. And then repeating the same process, Thompson sampling pulls a sample from these posterior distributions and assume that we obtain a sample of 0.6 for the first arm and a sample of 0.1 for the second arm. And in this case, Thompson sampling recommends us to pull the first arm. And again, since the expected return of arm 1 is large, we are more likely to observe a reward of 1 from this arm. And assume that this is indeed the case, and you observe a reward of 1 from this arm. Then Thompson sampling updates the posterior for the arm 1. And as you can see, it updates this posterior in a way that the expected return of this arm being closer to a value of 1 is much more likely to this arm having an expected return of 0, which also makes sense since we have observed that a reward of 1. After 100 rounds, as we gather more and more data from the reward distributions, the posterior distributions will start to concentrate around the true expected returns. So after this point, the posterior of the first arm is most likely to produce a sample that is larger than 0.75, whereas the posterior of the second arm is most likely to produce a sample that is smaller than 0.5. So this means that after this point on, Thompson sampling is almost always recommend us to pull the first arm. Therefore, we can conclude that at this point, Thompson sampling has determined the better arm and will recommend that arm after this point on.